Okay, so here we're simplifying this expression. I'm going to look at the radicand 90 and 40. That's the number under the square root sign. What I'm going to try and do is rewrite square root of 90 so that we've effectively taken the square root of all the perfect square factors. So what that means is I'm going to find the factors of 90. Let's find the perfect square factors, right? And to do this, I mean, sometimes they're easy to recognize, but a really great technique is to take the prime factorization. That means I just took 90 and said, okay, pick any two factors, any two. And that's what's so nice about this. You'll ultimately always find all the perfect square factors, regardless of what you pick at the beginning. So I picked 9 times 10. And then I break down 9 into two factors. And once I reach prime factors, right, a number that has only two factors, one in itself, I stop. And here with 10, the factors are 5 and 2. So that means that square root of 90 is equal to what? The square root of 3 times 3 times 5 times 2. And a great property here is that we can take the square root of each of these factors, right? And the product of those square roots will be equal to the square root of 90. So the square root of 3 times 3 times the square root of 5 times 2. We haven't changed anything here. We're just saying we're shuffling around the factors so we can break this number down further. It's still the same number. And this is a great property, right? That you can do this. You can, when you're multiplying, not when adding, but when multiplying, you can break a number up into its factors, take the square root of those factors, and you haven't changed the number itself. Why did I break it up this way? Well, I know the square root of 3 times 3, the square root of 3 times 3 is what? Well, that's just 9, right? The square root of 9 here, and the square root of 10, right? 5 times 2 is 10. I chose that because the square root of 9 is 3. Or the square root of 3 times 3 is just one of those 3's, times the square root of 10. So I've effectively rewritten the square root of 90 as 3 times the square root of 10. And this is going to be helpful in a moment. So here we have 4 times the square root of 90. Or, if we just said 4 times the square root of 3, 4 times 3, radical 10, or 4 times 3 times the square root of 10. I just substituted in this value in where we have the square root of 90. And that's what? Well, that's 12 groups of radical 10. And now we're getting somewhere. We're going to add this to radical 40. Well, the square root of 40, we can break that down in a similar fashion. That's equal to 4 times 10. 10 is 5 times 2. And 4 is just 2 times 2. So this means that the square root of 40 is equal to the square root of 4, or the square root of 2 times 2, times the square root of 10, or the square root of 5 times the square root of 2. And that equals what? Well, the square root of 4 is 2, and the square root of 10 we can't break down any further. In other words, there are no other perfect square factors. And notice what happens is here we have 12 times the square root of 10 plus 2 times the square root of 10. Now we can add these because we can treat the square root of 10 as our common grouping. So here that means we have 12 groups of square root of 10 plus 2 groups of the square root of 10. That's 14 groups of the square root of 10. It's kind of like when you have 12x plus 2x. Here that x would be the square root of 10. So that would equal 14x. This equals 14 times the square root of 10. It's just counting up the number of groups. So the goal in these problems is to get the same radicand, the same number under the root sign, and then you're able to simplify. That's especially when the case is that you're adding different terms here, right? This term and this term. All right, I hope that helped.